On the market today, one of the main ways in which ultra-low temperature chilling is achieved is through the use of an auto-cascade cycle, which is shown above. This system relies on a delicate and expensive blend of refrigerants that are designed to separate during normal operation. That being said, the system is kind of like a mixture of water and oil, and if a leak develops, the delicate balance of refrigerants can be easily upset. If the mixture does get upset, this entire system must be purged and recharged.
Our solution is a dual-stage cascade system, providing an alternate to auto-cascade and improves upon current shortfalls and reliability, and maintainability is improved. The high and low stages work in series, with the high stage providing the cooling necessary to maintain an efficient operation of the low stage, which then in turn chills a circulating process fluid. Both the high and low stages utilize a conventional refrigeration cycle with a few improvements to increase efficiency. First, looking at the high stage, key additions include the water cooling of the condenser, which allows for lower condensing temperatures and improved efficiency. Additionally, a suction line heat exchanger was added to optimize the values of superheat and subcooling. Next, looking at the low stage, which is coupled to the high stage through the cascade condenser, key components include a suction line heat exchanger serving the same purpose, as well as a desuperheater which reduces the thermal load on the high stage. Additionally, an expansion tank was added to limit the system pressure during shutdown to safe levels. Lastly, the process loop interfaces using the low temperature evaporator and simply circulates the chilled fluid, storing it in an insulated tank. Next, on to conclusions.
Our first major conclusion is that the projected production cost is about $12,000 per 3600 BTU per hour unit. Our next major conclusion is that scalable components will allow for an easily customizable system. By changing major refrigeration components like compressors and heat exchangers, a required cooling capacity can be achieved. Next, onto the recommended next steps. The first next step recommended is further testing to determine the correlation between temperature set point and cooling capacity throughout our operating points. The next recommended next step is to enhance the control scheme to allow for the integration of variable components. This will allow for greater system efficiency and for optimization at different temperature set points. We, as Team 16, would like to thank Fluid Chillers for their guidance and support throughout the project, Cleveland Cliffs for their donation of the steel paneling used in our design, and AWG for the nitrogen supply for both brazing and pressure testing.